In this video, I want to show you one way to choose the diameter of a pipe by optimizing its cost. The pipe is used to carry a fluid under pressure, and we want to build a simple model. We will consider a pipe, so let's sketch the pipe. We have something like this, a very simple sketch, and the fluid is passing through this pipe, and we will assume that we can associate the fluid with one density rho. Let's call it rho f, and then we can associate a velocity c to the fluid, and we can speak of average velocity, for example, average density. Then we will have a length for this pipe, and the pipe does not necessarily need to be straight, let's say. It can also have some bends and turns, but I think of it as being straight just for the sake of simplicity. And let's consider also the cross section of this pipe, and it will have some internal diameter, which is what we want to optimize. Let's say we want to find the diameter, capital D, such that we will minimize the cost. And I will try to explain more about this because there are other details hidden under the rug, and it's important to highlight these details in this case. Then we will have some thickness here, lowercase s for the pipe. And then let's try to make a model here, a model for the cost of this pipe, an investment, let's say. So I will call it I. This is the cost. I is the cost or the investment for the pipe. And this is equal to, I will use a parameter QP. QP is the cost per unit power, and I will explain to you a little bit more about the power. Then we have to multiply by the power to obtain the cost related to this power, quote unquote power. And let's say it straight away. So the power P is related to the energy per unit time that we need to pump into the system in order to move the fluid. So we will have, for example, some pumps in our system that will manage to move the fluid, because otherwise we cannot keep the fluid under pressure and we cannot really move it as we want. We need to have some power generated by the pumps that constitute our pumping system. So this is the overall cost that we have to sustain in order to be able to move the fluid inside this pipe. And then we also have the cost for the pipe. So we have some QT, some coefficient QT, which is a cost per unit mass of material that we need to use to make up the pipe. Then we have the density of the pipe times the volume of the pipe. So rho times V will be the mass of the pipe. Then we need to express this term, the power, and also this volume of the pipe in terms of the diameter D of our pipe itself. We'll assume that these coefficients here are constants with respect to the diameter, and all the other parameters are fixed. And the power generated by our pumping system multiplied by some efficiency coefficient, eta, I will call it eta, and this is, let's say, an efficiency coefficient which takes into account the losses that we have when the energy is transferred from the pumping system to the fluid. So not all of this power will go to the fluid, because some of it will be lost, and ideally we want eta to be as close to 1 as possible. And this will be equal to, in general, with this, we need to cover the losses, the energy losses of the fluid inside the pipe. And these energy losses can be obtained by using the volumetric flow rate that I will call Q. So this is volume per unit time, the volume of fluid which passes through this pipe per unit time, multiplied by the change in pressure that I will call it delta lowercase p, And this is the change in pressure inside the pipe. So the fluid, as it passes through the pipe, will tend to decrease its pressure. So delta P will take into account that decrease in pressure, but we have to assume that delta P is positive, so we are considering the absolute value of this. So this delta P here is thought to be positive. And you have to remember though that the pressure of the fluid is going to decrease as the fluid passes through the pipe. That's important. So that's why we need some pumps, or in general a pumping system, to cover for the losses that we have due to this decrease in pressure. So pressure has dimensions of energy per unit volume. So if we multiply that by volume per unit time, we're going to get energy per unit time, and therefore this is also power. So the dimensions of these two quantities on the right hand side and on the left hand side are exactly the same. Then, in fluid mechanics, there is a way to express the decrease in pressure, or let's say the change in pressure for a fluid which is passing through a pipe. And that is equal to some coefficient K, and I will call it K, and I will not talk about the details of this coefficient. In engineering, there are several ways to estimate this parameter. So they are not really rigorous ways, they are engineering ways. Let's call it like that. So it's not really something very rigorous, but it is possible to estimate this coefficient, and it takes into account the shape of our pipe. Then this decrease in pressure is proportional to the density of the fluid, and then it is also inversely proportional to the diameter of the pipe, and it is also proportional to the kinetic energy per unit mass of the fluid, which is the velocity squared c squared of the fluid divided by 2, and then it is also proportional to the length of the pipe. It is actually possible to derive this result a little bit more formally by using Navier-Stokes equations, but it is only possible for the case of a laminar flow, where this coefficient k has some well-defined expression, but I will not derive it here. That goes beyond the purpose of this video, but anyway, this formula, you should consider this formula to be in between rigorous mathematics and engineering. So this is more towards engineering than it is towards mathematics. It is closer to engineering than it is closer to mathematics, because this is applied by engineers also when we don't have a laminar flow, and also when this coefficient k is not equal to the case where the flow is laminar, and in that case you can express this in terms of the Reynolds number and whatever, but I don't want to get into those details. You can think of this as some kind of engineering formula. It is more practical than theoretical. And we need to rewrite this formula here because the velocity also depends on the diameter of the pipe, and a way to see that is like this. So the velocity times the cross section, let's call it A first, is equal to the volumetric flow rate Q, and A is equal to pi d squared over 4. So we can write C as Q divided by pi d squared over 4, like this. And we are going to assume that Q is a constant. So the volumetric flow rate is a constant, which means that the velocity will depend on the diameter of the pipe. So we can rewrite this expression as K rho F over the Q squared L divided by 2 pi d squared over 4 squared, and therefore we can write this as 8k rho f q squared L divided by pi squared d to the 5th power. And then let's also write the volume of the pipe Pt. This is equal to, by considering the cross section that we sketched here, well, the volume is given by this area here, because remember that we are interested only in the material that we are using. So the cost will be proportional to this kind of material, and we will multiply that by the length in order to find all the volume that we need, because the fluid is passing inside here, but we should not take into account also this volume here, because in here we have the fluid, so the material will be hollow in this part, and the volume can be obtained like this. So we take pi times, we get the external radius squared, so it's 2s plus d squared over 4. So this is the radius squared, the external radius squared, and I'm considering this actually. So if this is the center of this cylinder, I am talking about this radius here, the external radius, which is the diameter plus twice the thickness, and we have to divide that by 2. So if we square that, we get this, and then we have to subtract the internal radius, which is d squared over 4, and we multiply by L. So we can rewrite this as pi over 4, 4s squared plus d squared plus 4sd minus d squared times L. And this is equal to pi s squared plus sd times L. Now, we will make another assumption, and the assumption is that the thickness S is a fixed percentage of the diameter of the pipe. And this makes sense because the larger the diameter, well, there is more fluid inside the material, so inside the pipe, and therefore the thickness will have to be a little bit larger. And so we will assume that there is some kind of relationship S equal to a constant, which is a percentage, lowercase r times the diameter. And therefore we can rewrite this as pi times r squared plus r d squared times L. And now we can substitute what we found for delta P, Vt inside our formula for the investment. And delta P should be substituted here first to find capital P, the power, and then we substitute there. So the investment, or the cost, whatever you want to call it, is equal to QP times 8K rho F Q to the third power L divided by eta pi squared times 1 over d to the fifth power plus QT rho pi L r squared plus r d squared. Now let me call this coefficient here a, so this is a, and this coefficient here is going to be b. So we have a over d to the fifth power plus b d squared. And this is an interesting function because you can see that the larger the diameter, the greater will be this term, and the smaller will be this term, because we have more material to purchase, and therefore this cost here, this part of the cost will increase, but we have a smaller cost related to the pumping system. So we have less energy per unit time that we have to transfer to the fluid. I mean, this is simply due to this formula here for the decrease in pressure, which is related to the power here. So since delta P will be smaller if D is larger, also the power that we have to transfer to the fluid, thanks to our pumping system, can be smaller in general, and therefore there will be some kind of optimal value for D, which will minimize our cost I. And how to do that? Well, we simply have to calculate a derivative. So we have to calculate the derivative of the investment with respect to the diameter, and that is minus 5a over d to the sixth power plus 2bd. And let's try to find those values of d which will make this greater than or equal to 0. So in particular, this is true if minus 5a plus 2b d to the 7th is greater than or equal to 0, or d to the 7th is greater than or equal to 5a over 2b, like this. And since we are interested only in those values of d which are positive, of course, because it's a diameter, we can simply take root 7 of this. It basically means that if we take d equal to root 7 of 5a over 2b, where a and b we defined previously, this will minimize our function I of d. So this is a mathematical way to find an optimal value for the diameter of the pipe by considering all the other parameters well defined and fixed, so they do not depend on the diameter. This is a proper way to find this kind of diameter. There is some mathematics, as you saw, but this is more like an engineering way of approaching these kind of problems, because there are some assertions that we went through here in this derivation which are more related to engineering than they are related to mathematics. Even if we took a derivative here, whatever, but this is some kind of engineering approach.